Hi, welcome once again to our online tutorials. Today we're going to be discussing a very unique and fantastic topic, limit and continuity, right? That's what we're going to be studying today. So this is not like any other topic that you can just glance through or skip through the video. No, you have to concentrate. So get a lot of water, sit down, relax, get your writing material, then you are good to go. At the end of this video, you may be able to understand a quick review on algebra, function, coordinate geometry, but why do we need to study limits and continuity of functions, right? We know that functions are basically the heart of modeling of real-world phenomena. You use functions to model everything that has to do with real-life situation and show explicitly how one quantity differs from another, how one quantity is related to another one. So, for instance, we have discussed functions before now, but assuming I want to talk about functions in the light of continuity or limit. For example, let's take, for example, we have a function f of x. Let's take this simple example here. If it is sine x upon x, right? We have discussed the domain of this function. We have also discussed the range of this function. You can check the video on functions below, or in the next video, you will see more videos on function. Now, one may likely want to ask that uh, 0, we know for sure that 0 cannot be part of this function domain, right? It cannot be this part of this function domain because the denominator here is going to be 0, which we don't want that. Now, if we substitute some values for x, right, we'll find out that this particular value of x of this function is approximately going to be equal to 1. You can try that, substitute some value here for x, some value here for x, you find out that the whole of this function is approximately going to be equal to 1, right? Now, another important question to ask is what happens when the independent variables become very, very large, right? What happens when the independent variable becomes very, very large? For instance, as x gets closer to 0 in this case, you find out that this whole function tends to 0, right? The whole function gets to 1. Rather, as x tends to 0, this whole function tends to 1. The whole of this function is going closer to 1. As x tends to 0, the whole of the function that we have, the f of x, which is sine x upon x, will go to 1, right? Another important question is to ask is this function, what happened to it when this function becomes very, very, very large? For instance, if you want to talk about, there are some other function, the exponential function, right? We have this function. Let's say the function is a multiplication with another sine function, right? So what happens when t becomes very, very large, right? Now, you can use this to model damp simple harmonic motion, right? So as t becomes very, very large, the function itself become very, very small. You can try it by putting a very, very high value. Use your calculator, like try t, maybe 1000. You will discover that this function is diminishing, right? Is going to diminish. Now, the function is diminishing, which means it's approaching 0, right? It's approaching 0. Now, as x continue to increase, the function approaches 0, right? As t continue increasing. Now, we can say that it's increasing to infinity or whatsoever, a very, very high number, then the function is decreasing. Now, in both cases, this give us the idea of what limit is all about. What is the limit of this function? How is this function behaving, maybe at a point or as the value of t keep on increasing, right? So basically, that is what the concept of limit is all about. Now, for this particular uh, section, we are just considering it as a basic secondary school curriculum. So we are not going to go deeper into formal definitions, but this property of function is just what help you understand how you think about the function. As x increase or decrease, what is happening to the function, right? So that is everything about limit. For instance, if you have a set of sequence, which we have done when we are studying AP and GP, right? If this is a set of sequence, let's say 1, then the next is 1 all over 2, the next one is 1 all over 3, the next one is 1 all over 4, we have 1 all over 5, then continuously. Now you can see that as we keep on increasing the denominator, this function, they keep on decreasing. This is 0.5, then this is like 0.25. Can you see? So it decreasing. This function, as n increases, if this is a value for n, you can see that this function is going as far as 0, but it cannot be less than 0, right? This term cannot be less than 0, but it is decreasing. As we keep on increasing, we can have 1 over 1 million, somewhere, maybe 100 million, somewhere here. You can see that this function, there is going to be a value, but it is approaching 0. You may have 0.000000000000001 at the end of the day at some point in the number line, but it is not going to actually become 0, but it is approaching 0. That is just the idea of a limit. And if we represent this as n, we can say that 1 all over n, if it is defined such that n is just your counting number 1, 2, 3, 4 continuously, then the limit of this sequence, is going to be what? Is going to be 0, right? So we now define it using algebra and mathematical terms to write the limit as n tends to infinity of the function 1 upon n is equal to 0. Simple, right? So this is very, very interesting, and this is how we represent the limit of a function. Good. Now, we can actually say that this function tends to 0, but at every point in time, it does not touch 0. If you decide to graph this function, which you can use your graphic calculator, I have taught you that, and you can actually look at it also. Now, this function, if you are considering this function, the highest value here is going to be 1, right? This is your y-axis, and if this is your x-axis, you represent it by n. If you have 1 over here, 2, 3, 4, 5, let's say this is 1, 2, 3, 4, 5, then continuously, my 1 is going to be 1 over here, which we can mark. My 2 is somehow around 0.5, right? The second one. Then continuously, you will discover that this function is going to look somehow like this, right? Then you can decide to trace this function, but this function actually did not get to 1, then it is continually going in a diminishing order. Good. Now, similarly, we can say that if a function n goes to infinity, right? If it goes to infinity of this kind of function, if the function is 1 upon n to any integer, let's represent the integer or a real number by a, then it is also going to be 0. Why do we know that it's going to be 0? By simple algebra, you know that any number here raised to power n, in fact, it is going to go to 0 faster. For instance, if you take n raised to power 2, you can see that if we pick the same set of counting number, the first term is going to be 1, right? The second term is going to be what? 1 all over 4. The next one is 1 all over 9. You can see that it's even going to 0 faster. It tends to 0 faster. So, for example, we can now consider, let's take some other examples over here. Let's take some example. We can be asked to find the limit of n as n tends to infinity of the function 3n squared plus 2n plus 5, right? Then this is all over n squared, let's say minus 2. Now, looking at this critically, it's very simple to argue that if n is very, very large, then the largest term here should be 3n squared. If n become very, very large, the largest term here, sometimes we call it the dominant. We call it dominant, right? Take note of this. We call it the dominant. So this dominant over here, you should take note of this. The dominant over here is very, very important to always consider it when you are talking about how to ascertain the limit of this function, right? Now, while the dominant term in the denominator is this particular term over here, right? This particular term over here. Now, for now, we can just ignore the other terms and continue to do some very, very close algebra around this term. Now, by looking at this, I can just tell you that the limit is going to be 3. Now, how do I do this using simple algebra? What I need to do is just to use the dominant in the denominator to divide through all the terms of this particular function over here. So I'm going to have 3n squared upon n squared, this dominant that is in the denominator. Then I'm going to have plus 2n upon n squared, then plus 5 upon n squared. Now, the denominator, I'm going to have what? N squared upon n squared minus 2 upon n squared. Now, clearly, I know that this and this is going to cancel out. While from my indices, I know that this is going to cancel out this term. This and this is going to cancel out. So I'm left with 1 over here minus 2 upon n squared. While in the numerator, I'm left with 3, then plus 2 upon n plus 5 upon n squared. Now, clearly speaking, clearly seeing this, we can see that we know that 1 all over n tends to 0. So 1 all over n squared also tends to 0. We can then, by so doing, we can ascertain for fact that we're going to have 3 here. This term is going to be going to 0 as n goes to infinity, right? Because the limit you are looking for is the limit as what n tends to infinity, right? So if you pass this limit here, this particular term here is going to 0. This term also is going to 0. And this term also is going to 0. So we're left with 3 upon 1, which is just 3. And that is how I can ascertain for fact that this particular function over here, the limits as n tends to infinity is going to be what? 3. Good. Now, let's consider some other functions over here. Now, the function we have to consider over here is very simple. The function is, for example, we'll have the limit, right, as n tends to infinity of the function 5n raised to power 3 plus we have minus 1 raised to power n. Good. Then we have upon, let's say 4n raised to power 4, then plus 2. Good. Fantastic. If you are given this kind of a limit to work with, now how can you ascertain for fact how to go about it? Now, similarly, as we have the other one, right, it's very simple. As we have the first one, all we need to do is to do what? Is to divide every element here by the dominant in the denominator, right? So we have the limit as n tends to infinity of what? 5n raised to power 3 upon the dominant in the denominator is also n raised to power 3 plus we have, what do we have here? We have minus 1 raised to power n upon n raised to power 3. Then we have, this should divide 4n raised to power 3. This is 3. Then upon n raised to power 3. Then plus 2 upon n raised to power 3. Fantastic. Now, what do we see? We see that this element can cancel out. This can also cancel out. This is going to 0. If we take the limit, this is also going to 0. So provided if we are taking the limit, we'll have 5 over here. Then this guy over here is going to be 0. Then here, we're going to have 4. Then here is going to be 0. So our answer here is 5 upon 4. Now, this is very interesting and very simple, but we can go a step further to ask, what if we're trying to consider this function at a particular point, right? We're not taking it at infinity now. We want to get this function at a particular point. For instance, we have a function, say, we have a function, let's say we have a function of this form, f of x is equal to 2x. Can I get this limit as x tends to a particular point, maybe 1 or 2? It's very simple. You just pass the function. You just pass the point into the function, and then you get 2, provided this is a polynomial function. So let's continue with our lecture. We are going back to this point where we have the at a particular point. Now, the limit, when we're talking about series, it is beyond the scope of secondary school curriculum, but we are going to be advancing into other curriculum, right? So if we're talking about infinite series, right? For instance, we can take this particular example. For instance, if I have this is a straight line and I divide it by 2, if this is a straight line and everything here is going to be 1, 1. So if I decide to divide by 2, this point is going to be 1 all over 2, which subsequently I'm going to have over here, right? Then if I should divide the 1 all over 2 by 2 also, I'm going to have 1 all over 4. Is that not so? So I can decide to actually divide again by 2. So I'm going to get 1 upon 8, right? Now, if I should change also and divide this also by 2, I'm going to get 1 all over 16. Now, where would I stop dividing? At which point can I stop dividing? Now, this is actually what will give you an idea of what infinite series is all about. Infinite series, right? There are so many examples. So you can keep on dividing by 2. So at the end of the day, you're going to be having a series that look like this: 1 all over 2, 1 all over 4, 1 all over 8, right? 1 all over 16, and so on and so forth. You can have plenty series out of that. Now, if you look at that kind of series, we can now generalize it as, we can get this to a point where we have 1 upon 2 raised to power n, right? But this series, as is coming down, where is it coming to us? Where is it coming to us? This series is tending towards 1. Is that also? As you continue increasing the value of n. As you continue increase the value of n, you're coming towards what? 1. Good. So everything there goes to 1 as x goes to infinity, which you can actually check. Now, this kind of series is, when you take the sum of this series, you're going to get a geometric sequence in which each of the terms is just a multiple of the other one. We have discussed that before now. But here, let's just go over it again. When we talk about geometric series, right? GP, the progression, we talk about the sequence and the series, right? They were in this form where R is the common term. Good. So we can get up to A raised to power n, R raised to power n. Fantastic. Now, R cannot be 0. If R is 0, then you can call it a geometric sequence, series, or whatsoever. Now, we know that the sum of all these is just going to be A plus the second one multiplied by R, the third one multiplied by R squared, until you get to the last one. Is going to be A R raised to power n minus 1, which we already know. Now, if I want to derive the formula for the sum, I can just multiply this particular sum by r again. So I'm going to have AR then plus AR squared plus AR cube plus until I will get AR raised to power n. So I can decide to subtract Sn minus R, can subtract this particular equation from this. So I'm going to be left with only these terms, A raised to power R raised to power n, because this term here is going to be here, but this R over here is going to take out this subtraction. This is going to take out this. This is the previous term before R raised to power, before A raised to power n minus 1. Now this is the term that is supposed to be here. And this term is going to take it out. So I'm left with this term. So if I factor out xn here, over here, if I factor out xn over here, I'm going to be having 1 minus r. Then over here, I'm going to be having a into 1 minus r raised to power n. Is that not fantastic? So my Sn is just going to be a into 1 minus r raised to power n upon 1 minus r. Now, the condition here is that r should not be equal to 1 because this denominator will not be 0 at every point in time. It should not be 0, right? So looking at this clearly, if I am supposed to take the limit of this function, this particular function, Sn, as n approaches infinity, what do you think will happen to this particular part of this equation? This particular equation looks like this. It's going to be what? 0. Looks like what we have over there is going to be 0, right? So 1 minus 0 is 0. So the sum to infinity is going to be a upon 1 minus r. That is where you get the formula for the sum to infinity. It was using the concept of limit. Fantastic. Good. So now we are going further to now examine or take some more example. Let me use this part of this board over here. If I have the limit of this function as x approach infinity of the function 1 all over x, you have some seconds to think, what do you think this function should be? What the limit of this function will be what? As I keep on increasing the value of x, what will this function look like? Definitely is going to be equal to 0. Take, for instance, I have 1 all over 1 million. If I have 1 all over 1 million, then you can check the value of your on your calculator. You can see it's going towards 0, right? Now, if I want to grab this function, if I want to grab this function, let me see if I can do that over here. Now, if I want to graph this function, right? Now, that means that my function is going to be looking like, how will my function look like? My function is going to be looking like what? It's going to be looking somehow starting from 1, does not get to 1. Oops. I have a function looking like this, but definitely will not get to 1. It's just going all the way, right? All the way. This is my y-axis, this is my x-axis. So the function will look like that. You can use Desmos to see how this function will look like. Fantastic, right? Also, you can use this to know the concept of what we call the asymptote, right? Asymptote. So you can see that it does not get to 0, this function. X must not be 0. And also here, y2 should not, this function can never get to 1, but that's the limit of the function. Fantastic. Now, let's now go further to see some other example. Now, the example we have over here is to consider some limit at a point. Some limit at a point. Now, the limit at some point is given that you have a function. This function is x cubed. Now, find the limit as x tends to 2, right, of this particular f of x. So this is the same thing as saying I'm looking for the limit as x tends to 2. The function here is s cubed. Now, this is just going to be 2. Instead of putting 2 for x, all I need to do is to do what? Is to just put 2 raised to power 3, which I know is going to be 8, right? This is fantastic. So this is straightforward. Now, what if we have a piecewise function? A piecewise function, when I say piecewise, a piecewise function. For instance, I have f of x defined such that x plus 3 if x is less than or equal to 2, and then it is x if x is greater than 2. Good. Now, this kind of function is, they are very tricky, right? Because you can see clearly that the function has, for instance, here, it has y-intercept at 3, and then here the function is just x if x is greater than 2. So this is a linear. This is also linear, but let me see if I can graph this. The graph of this function should look like, let me get a straight line to draw this, right? So I have this. So for instance, so if you have this, now you can see that this function has intercept at 3 and is linear. So continuously is going to go this direction, right? This is going to go this direction also. Fantastic. But the second one now, it started if it is greater than 2, right? The condition is that if it is greater than 2, so this function is going to start somewhere around 2 and also 2, that's somewhere around here, right? It is greater than, so it's open. So this one too is going to go this way, right? Then this particular graph cannot be this long. Why? Because at immediately it gets to 2, there is a break. So I can take it out and say that this function, when it gets to this particular 2 over here, right? When it gets to this particular, that is a jump, right? That is a jump. This particular point is 2,5, while this particular point is 2,2. Now, that is a jump, right? This is the negative part of my graph. 2, this is should be -3, this is -1, this is 0, this is -2, continuously. You know how the graph should look like. You can actually use Desmos to plot this. Desmos.com. This is a graphic calculator, free online. You can use it to graph this particular function, right? So let's analyze this function. That is a jump. There is a jump over here. So the question is, what can you talk about this limit of this function? We have seen that there is a jump as x is approaching this function from the left-hand side, right? The highest you can have is 5. So as x value gets closer to 2 from the left, the value of y approaches 5. Now let's consider the other part. But as x value gets closer to 2 from the right-hand side now, the y does not approach the same 5. It came down to 2 instead, right? So in this case, we can say that the limit as x approach 2 of this function that we have over here, of this particular function, it does not exist. Why? Simply put, as I approach this function from the left, as x, the value of x gets closer to 2 from the left, the value of this function approaches 5. If you plot this very well, you will see that here is 5. I'm not using a scale, but you can notice it's like 5. In fact, it is 5 if you use a graphic calculator to do this, or you put some value for x over here. You will discover that at x is equal to 2. If I put 2 over here, I'm going to get 5, right? So if I put 2 for x here, the value here is going to be 5. So it's actually 5. Now, so sometimes we are asked to analyze the limit of this function at a point in which the domain is not even specified. For instance, this clearly does not exist. Sometimes you can be given a function. Let me give more example. A function, the function can be x squared minus 9 upon x minus 3. And we are asked to find this limit as x equal to 3. So I'm looking for this limit as x approaches 3 of the function x squared minus 9 upon x minus 3. We can see that clearly this is not supposed to be part of the function domain at all. If I put x equal to 3 here, I'm going to have undefined function over here. So, but clearly I can see that the numerator is just a difference of 2 squares, right? Difference of 2 squares, while the denominator is x minus 3, and I'm looking for this function at s equal to 3. The difference of 2 squares says I can have x plus 3, right? And x minus 3 upon x minus 3. It's clear this is how to represent difference of 2 squares. So I can take out this, and if I now pass the limit, because here I have the limit as x tends to 3. If I take the limit at this point, I'm going to have 3 plus 3, which is just 6. So you can see that when we simplify the function using the difference of 2 squares, we have a non-zero factor, x minus 3, which if we cancel out, right, we're going to be having the limit at this function to be near 6. So now, whenever x is near 3, the value of this function is near 6. Hence, near the x value 3, the function takes values near 6. So we can actually say the limit of this function is 6. So if you decide to graph this on a graphing calculator, this particular function, right, is looking as the function x plus 3, right? This function and this function is going to be the same, but with just one particular discrepancy. The intercept here is going to be 3. Likewise, the y-axis, but here we're going to be having at this point 3, where x is equal to 3, this graph is going to having a hole. It's going to be having a hole, right? If you decide to use the graphic calculator to do this, you will discover that at the point x is equal to 3, when it's reaching the point 6, you're going to have a hole over there, right? You're going to be having that hole. This is going to be a straight line. Then you're going to be having a hole at the point 3, 6. When x is 3, the value of the function is actually 6, but there is a hole because if it is at 3, it is undefined. So you're going to be having a hole at that particular point. Fantastic. Let's take one more. So we have the limit of the function x minus x tends to 2. The function is x squared minus 3x plus 2 at x squared minus 4. Clearly, if we put 2 here, it is undefined, so I can factor out the numerator and the denominator. If I factor out clearly the numerator, I'm going to have x minus 2 and x minus 1. You can check the video on factorization, but it's simple. Since the coefficient here is 1, I'll just look for two numbers, I'll multiply, and I'll get 2. If I add them together, I get minus 3. They are just minus 2 and minus 1. So it's straightforward. But other factorization, you can check the comment section or the next video to see how to factorize. Then here I'm going to be having 2 minus x minus 2 and then x plus 2, because this is just difference of 2 squares, right? So this can take out this, and I'll be left with taking the limit of this simple function over here, x plus 2. And now if I take the limit as x tends to 2, I'm going to be having 2 minus 1 upon 2 plus 2, which is just 1 over 4, right? So clearly this exists. Good. If you decide to plot the graph also, you're going to be having a hole at x is equal to 2. You can try that on your own. Fantastic. Now, we are going to go into another example whereby we are going to be taking the limit at both the left-hand side and at the right-hand side. So for this particular example, let me take this particular function over here, x minus 1, right? Clearly, it is not defined. This is not defined at s is equal to 1. This particular function will not be defined. As we take values close to it, but let's consider taking value greater than 1. If we take value greater than 1, the value of this function are very large and they are going to be positive. What do I mean? If I take values here greater than 1, so for example, I take 2. If I take 2 here, we have 2 minus 1. So we have 2 upon 1. If I take another, let's say a big one, like 10, I'm going to have in 2, 10 minus 1 is going to be 9. Good. Now, why if we take value close to 1, but in the negative direction, less than 1 now. Let's take values less than 1. So over here, if I take a value less than 1, negative direction, I'm going to have something like 2 all over less than 1, like minus 2 minus 1. You can see that the value of this function, they are very, very large. They are going to be large also, but now in the negative direction, right? So we can simply write this, that the function 2 upon x minus 1, as we keep on increasing the value of x to the positive side, this guy is going to positive infinity as we take x going to 1, but now we're considering the positive aspect, right? Similarly, we can have the value of this function, x minus 1, is going to negative infinity as x tends to 1 from the negative direction. So the notation here simply means x approaches 1 from above. For this, x approaches 1 from above, right? Why? For the other one over here, it simply means x approaches 1 from below. Fantastic. Thus, the function 2 upon x minus 1 has a vertical asymptote as x is equal to 1. If you plot this function clearly, this function will look somehow like this. Use your decimals to do that. You have 0, you have 1. The function never touches 1, right? So this function is going to be looking somehow like this, and then it's going to be looking like this, right? So it's going to have a vertical asymptote at what? At x is equal to 1. It never really touches 1. So that is how it means. But you see, as you approach from the left, it's coming to 1, but it's going towards the negative. And if you're approaching from above, it's going towards 1, but now it's going to 1. Can you see that? But it never really touches 1, and then the function increases. So that is what you have about that. Fantastic. So you can try some other examples and exercises on your own. But for the sake of this tutorial, let me take a clear example before we consider continuity. For instance, I have this one is very simple. We have what is the limit of x as it goes to 0 of the function x squared plus 4, right? S squared plus 4. Then minus 2 upon x squared. You can see we can't take the limit to 0 at this point. So we have to do some little algebra to make sure we get rid of this x in the denominator. And the simple way we can do this from SOLD, which we have done, I think the third video on this particular sequence of video is to rationalize. So how can I rationalize? I will just rationalize, in this case, the numerator, right? We can rationalize the denominator or the numerator by multiplying both sides by the conjugate. So what's the conjugate of this? The conjugate is very straightforward and simple. This is 2 plus 4. Then it's going to be plus 2, right? Because we have negative here. So the conjugate is going to be having a positive, right? I think it's straightforward and simple. So we are going to multiply all these terms. But if you look at it, we have not done anything to this particular equation. We can just cancel out, right? So here, all we need to do is to now multiply everything together. We can multiply this and this is going to be x squared plus 4, but this all is going to be squared, right? Fantastic. So this and this, we're going to be having plus 2 into, what do we have here? We can have x squared plus 4, right? Fantastic. Then this and this, we're going to have negative 2 into the same thing. Then this and this, we're going to be having minus 4. 2 multiplied by 2 is 4. Now, the idea behind rationalization is just to get rid of the radicals. So this is going to go out. You see that there's no more radical over here. But here we have x squared upon what we'll have here is x squared plus 4, then minus 2, right? So we have minus 2 over here. Now, so what do we have next? What do we have over here? Now, it suffices that we are going to have the limit as x tends to 0. What is going to remain here will be x squared. Here, we are going to be having plus 4. This is gone, this is gone. Here, we are having minus 4. Then what is on the numerator is going to be x squared. Then we are going to be having square root of what? X squared plus 4. You understand? Because this guy is supposed to be multiplying this. So this guy over here multiplying all these elements over here. So we are going to be having this, right? So technically, what we are going to be left with in the numerator is going to be x squared, because 4 minus 4 is going to be 0, right? So what we have in the denominator is s squared. Well, we're going to be having x squared